Hi folks, welcome to the Key Concepts Review for Chapter 2 of Math 521B, or Pre-Calculus 11. We're looking at triangles in this one, specifically sine law and cosine law. If you want to take a look at the disclaimers there, you'll see what this is good for and maybe what you might want to look at other online resources for. Also, there is a downloadable copy of the notes in the video description below, so you may want to download that and follow along with the presentation. Here we go! Right-angled trig review. The things that you need to know are Pythagorean theorem, which we all know by now. C squared equals a squared plus b squared. And SOHCAHTOA. So the idea that the sine of some acute angle in here is the opposite over hypotenuse. That the cosine of some angle is the adjacent over hypotenuse. And that the tangent of some acute angle is the opposite over adjacent. These are all only good for right-angled triangles. And then there are some general principles for all triangles. The angles in a triangle add to 180, and larger sides are across from larger angles. And similarly, smaller sides are across from smaller angles. Those are some things we want to have a good intuitive grasp of as we move forward. Cosine law. We're not going to prove it here, but it is given in your formula sheet, and you've probably done it in class. Here we go. C squared equals a squared plus b squared. It looks like Pythagorean theorem with a little correction. The thing that you need to know is, number one, this is an angle. And c squared and c are across from each other. Okay, this is the side c, and the big one is the angle c. So across from each other. Okay, that's a really good form of the cosine law for finding angle, or for finding sides, rather. Good for finding sides. If you want to find angles, it would be nice to rearrange this so that it's solved for cos c. So let's move the 2ab cos c to the other side. I'm just adding it. And let's subtract the c squared from the left-hand side. From here, we could divide by 2ab. And we'd have a form of the cosine law that is a little nicer for finding angles. Now again, these are across from each other. So the letters aren't really that important. It's just the idea that the angle and the side that gets subtracted off are across from each other. When you put this in your calculator, you may want to use some extra brackets to make sure that things are grouped appropriately. So the question is, when do I use cosine law? You use it if you know two sides and the angle between them, or if you know three sides. Let's take a look at a couple of quick examples. So in this one, we want to find x. We know two sides and the angle between them. Yes, we can use cosine law. And here's how we'd set it up. X squared, the side we want, is across from that angle we know. That's good. It's going to be a squared plus b squared. Doesn't matter which you call which. Minus 2ab cos of 40 degrees. From there, we just throw it all in our calculator. So 12 squared plus 15 squared minus 2 times 12 times 15 times the cosine of 40 degrees. I'll just double check that I'm in degree mode. Yep. So cos of 40, did we type it in? Close brackets. Boom. That gives us x squared is 93.2 roughly. And finally, we're going to need to square both sides. Square root, rather, both sides. Not square. So I'll go the square root of the answer. And it gives us 9.66 to 3 sig figs. Let's see, were there units? Yes, there were. They were centimeters. And even though the diagram's not drawn perfectly to scale, it does look like we should have a smaller side there. So things are probably good. All right, the next one we're looking for an angle, and we know all three sides. So cosine law is good for this. I think we should use this form of it. Okay? And you can either rearrange the original up here to that form, or you can memorize this form. It's not particularly difficult. You just subtract off the side that's across from the angle you want. Okay, so let's figure it out. We'd have cos of x is 11 squared plus 13 squared. It is important that we subtract off the 18, okay, because that's across from the angle we're interested in. All over 2 times 11 times 13. When I do that in my calculator, I'm going to make sure things are grouped properly, so I'll put some extra brackets around it. So 11 squared plus 13 squared. Oh, I said I was going to put brackets. Let's do that. 11 squared plus 13 squared minus 18 squared, close brackets, divided by 2 times 11 times 13, close, close. Exactly how I had it written down with those extra brackets. And it gives me negative 0.11888. Okay, but that is not the angle. In order to find the angle, we need to do the inverse cosine. And rather than type it out again, I'm just going to tell my calculator inverse cosine of the answer you just found. And then it gives me 96.8 degrees. And that looks somewhat reasonable. Again, it's not drawn perfectly to scale, but it's a fairly big angle across from the biggest side. Okay, sine law. We'll look at it for finding sides and for finding angles. It's given like this on your formula sheet. Sine A, remember big letters are angles, equals sine B over B. This is telling us that it's true throughout the triangle, but really we don't care about any of this. When we have an equation, we're just going to want one equal sign in it. Okay, so this is given. And it's good for finding angles. If you wanted to find sides, it would make more sense to flip the whole thing upside down. So A over sine A equals B over sine B. Also true, better form for finding sides. And we're going to start with finding sides. So what's nice about this form is that you put the thing you're looking for, the side, first. When do I use cosine? That should say sine law. You use sine law if you know or can easily find the size of an angle and its opposite side. So that means if you know a pair, the value of this angle and this side. Let's put it to use. So suppose we want to find x on this triangle. Can we use sine law? Let's see. We know a side and its opposite angle. Yay! We can use sine law. And here's how we're going to set it up. X, the side I'm looking for, over its opposite angle, the sine of its opposite angle, equals the side we know over the sine of its opposite angle. Just multiply both sides by sine 50. And we get this. X equals 12 sine 50 over sine 60. And all I need to do is throw that into my calculator. So 12 sine 50 divided by sine 60 gives us roughly 10.6. Again, we ask ourselves, are there units? Yes, there are. So that's 10.6 meters. Okay, the next one does not look good. Let's look at this. We know two angles. We don't really know two sides in an included angle. It doesn't look like we can do either sine or cosine law. But on the last slide, we said we use sine law if we know or can easily find a pair. That means a side and its opposite angle. In this triangle, the last angle over here, let's call it theta, is going to be 180 minus the other two angles. Because the total angles in a triangle have to add up to 180. So if we do that, we'll get 58 degrees. So we don't despair, we just see, well, there must be something we can do. And at this point, yes, we know a pair. I set it up. The thing I want over the sine of its opposite side, side I know, over the sine of its opposite angle. Throw it into the calculator and see what we get. 23 sine 55 divided by sine 58. Lovely. 22.2-ish. And there are no units here, so we could just say units. This leads us to finding angles with sine law. And this sometimes is made up to be a big deal. It's really not that big a deal when we try and actually solve some of these questions. I've got an approach here that you may find helpful, or you may find what you've done in class helpful. Here's the problem. If we use our calculator to find the sine of 30 and 150 degrees, well, first of all, I know the sine of 30 is a half for my special triangles. I wonder what the sine of 150 is. Oh dear, it's also a half. So it turns out that supplementary angles, that means angles that add to 180, have the same sign. Therefore, if we know that the sine of x is 0.5, or a half, we don't know whether the angle is 30 or 150. That's never been a problem for us in grade 10 with right-angled triangles, since all the angles are going to be less than 90 degrees. But in non-right triangles, we need to be aware of the issue. And here's what we're going to do to illustrate that. We're going to draw a triangle with the following properties. Angle A, I'm going to make A here, is 30 degrees. And goes out like this. Now the side that corresponds to it that we're making here is side little b, which is 7. And then I know that side A is 5 centimeters. So that's a little smaller than the blue one I just drew. So maybe the triangle looks like this. Okay? Let's assume this is all perfectly to scale. You could do this with a ruler. I could draw the triangle that way, and this would be angle B here. Or I could have made my 5 centimeter side look like this. In other words, it's ambiguous. We don't know which one we're talking about. There's not enough information to tell us. So the triangle could be drawn two different ways. That's what it says at the bottom. Either one is appropriate. The look of the triangle is ambiguous. Now, given that, let's still try and figure out what's going on. So A would be 5 in either case. Okay, and these are centimeters. This angle here is 30 degrees. B is 7 centimeters. So what it said in the formula booklet was this. Let's just swap that around. Sine B over B equals sine A over A. Let's sub in what we know. We don't know what the size of angle B is. We do know that its side is 7. We're looking at sine 30 over A, which is 5. I could multiply both sides by 7. And that'll give me 7 sine 30 over 5. And I could work that through in my calculator. Or I could know that the sine of 30 is a half. Gives me 0.7. Okay. Now we know that the final angle is not 0.7. The way we find the angle is by doing the inverse sine. And that's going to tell us that the angle is, well, let's see, inverse sine of 0.7, 44.4. Okay, well, that does look like what it is in this case. If it were the big triangle like that, this will be 44.4 degrees. The other case, though, would be what happens to angle B if we're in this situation. And we said supplementary angles have the same sign. So the other possibility is that B is 180 minus that 44.4 degrees. Okay? And if we work that through, we're going to get 135.6. Those are the two possibilities, and we don't know which is appropriate. In fact, they're both appropriate for the amount of information we were given. So this sounds like a big pain. Sometimes it's suggested that we make scale drawings, and that's really good to see how this looks. But I've got an algebraic technique that I'm going to show you here that may save some trouble. So in triangle trigonometry, using the sine law can lead to ambiguity as to whether we have an acute or obtuse triangle. Whenever we use inverse sine in a non-right triangle, we have to consider two possible angles. The one your calculator gives you and its supplement. We only have to consider them. There are many ways to conceptualize these problems. Here's my patented approach. Number one, if you don't have to use sine law, don't. Cosine law has no ambiguity. So in that way, it's kind of better. Anytime you use inverse cosine, consider both possibilities. And then think about what's illegal in a triangle. If one of your possibilities makes your triangle add up to more than 180, cross it out. It's no good. If the calculator says error, then the triangle was impossible to begin with. Sometimes I'll suggest doing a garbage diagram, which is just a terrible diagram of what's going on so that you can at least set up your sine law. But beyond that, making a really accurate diagram can sometimes be time consuming. It's a good practice, but you have to make a really good one to be able to say something definitive about the triangle. Let's try this technique. So if I've got A is 25 degrees, A equals 7 centimeters, B equals 11, find angle B. Okay, so I'm just going to make a garbage diagram. 25 degrees, I don't know, somewhere over here. There's A, that's 7. B is 11. What's angle B? Want to figure this out. Okay. So that may or may not be how it's actually drawn. There may be two ways that it could be drawn. I'm actually going to scratch this diagram out when I'm done. I want angle B, so I'll say sine B over 11 equals sine A, which is 25, over its opposite side. So sine B is 11, sine 25 over 7. We head to the calculator. Gives us 0.664. We know that we have to do the inverse sine. So inverse sine of that answer gives us 41.6. Or 180 minus 41.6. These are the two possibilities I'm considering. Okay, now that I've considered them both, let's see if they're both appropriate. If B is 41.6, does it go over 180 degrees? No, it's fine. This one works out Great. If I have 138.4, let's see, is 138.4 plus 25 bigger than 180? No, it's fine. Both of these are answers. Now, they result in the triangle being drawn different ways. So if I had the 41.6, I'd have a 25 degrees here. I'd have a 41.6 here. If it were the other one, I'd have a 25 degrees here. And then I'd have a giant 138.4 angle right here at B. But they're both triangles that satisfy those initial conditions. So I checked them, and they're both OK, because they didn't exceed 180. Let's try another one. A is 56. OK, so there's my 56 at A. A is 13.5. So that's across from angle A. B is 16.8. Find angle B. So sine of B over B, which is 16.8, is going to be sine of 56 over its opposite side of 13.5. Let's see what happens. I've got 16.8 sine 56 divided by 13.5 gives me roughly 1.03. Now, some of you might be thinking at this point, hold on, that's trouble. But if you're not, that's okay. We'll do inverse sine of that answer. And it says there's an error. It doesn't exist. So angle B does not exist. The triangle is impossible. If you can draw this triangle to scale, scan it in, send an image to my email, I'll send you $100. But I think my $100 is safe. So the garbage diagram I made was just that. It was a garbage thing. We didn't know if it was possible or not. Let's try another one. A is 30, A is 12, little side A is 12, and B is 10. So 30 degrees. Okay, A is the bigger side here. It's 12, 10. Let's see what happens. There's big A. There's little a. There's B. Interested in. And it doesn't matter what the letters are. It's still going to be the same process. So sine B over 10 equals sine of 30 over 12. Sine B times both sides by 10 is 10 sine 30 over 12. Send that to our calculator. 10 sine 30 divided by 12 gives us 0.416. So B is the inverse sine of that. B is either 24.6 degrees, or B is 180 minus 24.6. 155.4. I'm considering both options here. And I do this every time I use inverse sine. Now let's check it out. If I have one side that is 24.6, one angle rather that's 24.6, and one that's 30, that does not exceed 180, so that's fine. This one's all good. What if I use the other one? If I have 155.4 and 30, is that bigger than 180? Is that going to be an impossible triangle? Yeah, that'd give us 185.4 degrees, which is too many degrees for a triangle. So this one only has one solution. But we can, by considering both, we can find that one solution. Here's the last one we'll take a look at. It's just a difference in notation. So say we have angle B is 65. And then we say BC. Side BC is 14.6. I always cross this out and call it little a. Big AC, that's side B. Okay, it's the letter it doesn't contain. Okay, and that tells me that somewhere over here there's a 17.4. I want to find A, which is this, and it's going to be 14.6 for little a. We'll set it up. We want to find the sine of A in this case. So sine A over A, which is 14.6, equals sine 65 over 17.4. Okay, we'll do our regular stuff. We'll figure out what the sine of A is. And I ran this through in my calculator already. It's 0.760. I do the inverse sine, and I get either angle A is 49.5 degrees, or angle A is the supplement of that, 130.5. Okay, let's check it out. If I had an angle of 49.5 and 65, my triangle would be fine. It would not be bigger than 180 degrees. If I had 130.5 and 65, that would be no good. I'd be up around 195 degrees. That's too big. Once you've determined the number of solutions in the different cases, you might be asked to solve the entire triangle, and that would just be using sine or cosine to find the remaining side, and using the fact that the angles add up to 180 to find the missing angle. So the short version is, if you use inverse sine in a non-right triangle, consider two answers, and then scratch the ones out that take you beyond 180. There are other analytic approaches that are great as well. This is the one I prefer. Okay, so the question becomes, what do I use where? You use cosine if you know two sides and the angle between them, or you know three sides. Sine if you know the measure of an angle and its opposite side. So in this first one, we know three sides. This is cosine. And you might want to pause it here and just decide on each of these. In the next one, what do we know? We don't seem to know very much. But we could easily find the last side. It's going to be 180 minus 120 minus 38. And once we know that, we know a pair. So this is going to be sine. C. Do we know a pair here? Yep, we know the angle and its side that's across from it. And in D, we know two sides and the included angle, or angle between. So this one was sine, this one will be cosine. I'll just have the solutions pop up here. And there they are. Notice in C, we considered the two possibilities, and then we scratched them out. The last thing we'll look at are some trig word problems. From last year, from grade 10, you'll know that angles of elevation and depression are angles measured with respect to the horizontal. But this is something that gets messed up a whole lot. So they're just like your reference angles in standard position. They're compared to looking straight forward. Okay, so this here would be an angle of elevation. This 62 down here is an angle of depression. Angles of elevation and depression are sometimes called angles of inclination or declination, or simply just angles of inclination. The big idea is you need to measure with respect to the horizontal. One of the sides where that angle is needs to be the horizontal. So just as a quick throwback to grade 10, we've got a 12-meter tree that casts a 5-meter shadow. All right, here's our tree. My artistic skills are not very good. It's 12 meters tall. It casts a 5-meter shadow. Find the angle of the elevation of the sun. So somewhere up here, there's the sun. Okay, and it's casting that shadow. The question is, where do we put that angle of elevation? And what I'll see a lot is people doing this. I'm going to write right away, bad, don't do this. Look, you don't have the horizontal involved there. You've only got the vertical, the tree. That's no good. If we want an angle of elevation, we're talking about an angle that involves the horizontal. It must be this. Okay? And from there, since this is right-angled trig, you could use SOHCAHTOA. Okay, so this is opposite, adjacent. We can say that tan theta is 12 over 5. Theta is the inverse tan of 12/5. And then whatever that is. It's about 67.4 degrees. You can check that in your calculator. Let's do a fairly involved question that involves drawing the situation, which you'll likely have to do on your math exam, and involves some non-right angled triangles. Here we've got a tower that's at the top of a hill, and the hill is 100 feet tall. From a point at the bottom of the hill, the angle of inclination to the base of the tower is 35 degrees. The angle of inclination to the top of the tower is 43 degrees. How tall is the tower? Okay, so step one here needs to be to draw a diagram. So we've got a hill. There's the hill, and it's 100 feet tall. We've got a tower on top of the hill. Here's the tower. Okay. From a point at the bottom of the hill, right here, the angle of inclination to the base of the tower is 35 degrees. So that means this angle right here is 35 degrees. The angle of inclination to the top of the tower is 43 degrees. So this whole angle here would be 43 degrees. How tall is the tower? We do have some right angle stuff happening here. We're looking at the height of the hill, and we're assuming that the tower is going straight up and down. I think sometimes it's really helpful to put in some letters here. So right here, let's call this the point A. Here's B. This is C right here, and D. Those are all the vertices that we have. And from there, we might think we want CD. And what triangle is CD in? It's in triangle ACD. But we don't know much about ACD. So that's a problem. If we could find one of the shared sides, though, that might help. So if we could find the measure of a shared side, and what's the shared side here? It would be AC in this case. That might help. Okay. And we can probably find AC. AC is in the triangle ABC. So let's split apart and take a look at the triangle ABC. And this is where having the letters helps, because you know which triangle you're looking at. So in this triangle, we've got 35 degrees. We've got 100 feet right here. That's a right angle triangle. We can use SOHCAHTOA. This is the opposite. This is the adjacent. This is the hypotenuse. And what we want is the hypotenuse. So what uses opposite and gives you hypotenuse? Sine. Sine 35 is going to be opposite, which is 100, over the hypotenuse, which is AC. We could call it the measure of AC. We won't worry too much about the notation. We want to make sure that we know which side it is we're finding, though. Okay, so we rearrange that equation, and that gives us 100 divided by sine 35. That had better be a number bigger than 100. And it is, 174.34. I'm going to keep a bunch of significant figures at this point because that's not my final answer. Okay, so does that get us any further ahead? I think it does. It finds us this side here. Now we can revisit triangle ACD. Revisit ACD. Okay. Which looked kind of like this. CD is what we want. Okay. We now know that this side is 174.34. We could easily reason out that this little angle here is 8 degrees. It's 43 minus the 35. So there's 8 degrees. And the CD is what we want to find. We still don't really have enough information. If only we could find another angle. If we could find this angle up here, we'd be all set. We could use Sine Law. So that might lead us to take a look at the big triangle. ABC, or ABD rather, has a 43, a 90, and that means this missing side up here, or missing angle rather up here, is going to be 47 degrees. And that fits in right here in our triangle ACD. Okay, so we do have to do a little sleuthing here. And there's no way that we can say there's a method for every single one. It's just cataloging what you know and what you don't know, and then trying to get a little further ahead. So X, or CD, is the thing we want. Look, we know a pair, a side, and its opposite angle, so we can use Sine Law. So CD over sine 8 is going to be 174.34 over sine 47. Let's work it through. And we'll send that to the calculator. And it's going to give us roughly 33.2 feet. Meaning the tower is 33.2 feet tall. That gets us to the end of the triangle trig in 521b, or Pre-Calculus 11. Hope that you found this helpful. It would definitely be worth finding some of these word problems to take a look at, because you're very likely to run into one on your exam. Good luck, folks. Take care.